James. I'm one of the speakers and one of the organizers of this conference. I hope that you've all had your fill of meat pies. There are still plenty of them outside. I thought, they're really, really good. I, in fact, have some up here to nibble on as I give my own presentation. So I said I'm one of the organizers, and that allows me certain privileges. As you see, I like to start all my talks with a little tweet. So I can tweet myself here. And then, considering that I run the Twitter feed for this conference as well, I can retweet myself in the other window.
I think a round of applause is warranted.
So there we go. And then what I'll do is I'll now retweet myself. Oh, there we go. I'm there. And we'll get started. So I'm James. You may already know me or know of me. I speak at a lot of conferences. I gave 15 talks at 7 conferences in 5 countries last year. I also run this. This is CPython. It's the world's largest Python meetup group. If you go to meetup.com and you look, we are at 4,636 members. It is an amazing group and something that I'm very, very proud of. I also have a blog at seriously.don'tusethiscode.com. I thought it's good to have the disclaimer in the title where I talk about some really preposterous things you could do in Python, such as bytecode patching and whatnot. Today's talk is going to be a little bit simpler than that. But before I get into that, I want to do just as a very quick show of hands. I'm going to flash some things on the screen, and I want you to say, raise your hand if you understand what's going on the screen. So who knows what this is? I hope everyone. OK, who knows what this is? OK, who knows what this is? Oh, very easy. Who knows what this is? OK. Who knows what this is? Nobody knows what this is.
That's funky.
So this is funky, but it's actually very simple. It's actually the same thing as this. So pretty straightforward, right? Which is, it turns out, the same thing as, come on, it's a joke. Look, what is that? Which is the same thing as that. So there's actually quite a bit of depth and quite a bit of interesting material to generators. And generators, I think, are one of the most notable and the most interesting features of the Python programming language. Generators conceptually exist in many other programming languages, and you may be familiar with them by some other means. I think that in Python, they're the perfect combination of mechanism and syntax for expressing and reconceptualizing your code in a very, very compact, very simple, and I like to say that when people write functions, they oftentimes pad their parameter list with Boolean parameters, right? And they say, OK, I'm going to take some switching in my function. I'll pass in a true or false, and in the function, I'll put in some switching. And then they think, well, let me move one order higher. And instead of having that switching, I'll pass in a function, and the function will handle that modality. I think that generators are the next stage of conceptualization beyond basic functional programming, where you can take a function and you can fundamentally restructure the way that you write it in such a way as to make it simpler and to also add flexibility and to free yourself of certain presumptions that you have. So let me get started. I have my slides here. They're on GitHub. If you go to github.com/DUTC, that's don't use this code. I'm from Texas, and people often mistake my handle online for Dutch with an H missing. So it's either don't use this code or don't use this code, Haas. OK, good. I got at least one laugh out of this talk. And you can see at the top, generators, and the notes should all be here. So if you want to follow along as you go. So usually in this talk, I start with some very basic formal differences between generators and functions. And when I mean formal, I mean it in the sense of the form of it, right? A function is merely some structure, some syntax, which has this return keyword that returns some values. There's input and there's output, and they happen, you input once and you output once, and that's all there is structurally or formally. And a generator is very similar looking. In form, it's very similar, but instead of that return, you have a yield. And instead of calling it and returning and receiving your output values by calling it, you call it to construct a generator instance, and then you iterate through it to get your values. So now, fundamentally, you've taken one semantic building block that represents a computation. You enter that computation by passing formal parameters. You receive the result of that computation immediately, eagerly. And a generator, where you have a computation that you start, you initiate or instantiate, and then receive chunks of that computation lazily as you ask for them. So that's the first fundamental difference between a function and a generator. This contrast between eagerness and laziness, and this contrast of the basic syntax. One of them is called and one of them is iterated. And to demonstrate one very interesting part of what the Python programming language is really all about, very fundamentally really all about, I like to talk about iterability and callability as the two fundamental protocols of the Python programming language. So other programming languages are built on a very nice theoretical foundation. Haskell is built on a very rich theoretical foundation, whereas Python is built on a more practical foundation. And if you really look at Python and really look at the way that we interact with objects in the Python programming language, what you see is that it's a language that's built off of a set of ad hoc protocols. The most important of those two ad hoc protocols are iterability and callability. And one way that we can see how fundamental they are is by seeing just how generic they are. In addition to these two protocols, we have a protocol on top of numbers. There's the ability to, in CPython itself, you have these substructs for numbers, for sequences, for mappings, and they expose these other fundamental protocols. A mapping is you have some object and you get elements out by a key lookup. And sequences, you can get each element sequentially and you can look at the length of it and so forth and so on. And numbers, you can take objects and you can manipulate them as though they look like numbers. But more fundamental than those protocols are those of iterability. So here I have an example of, actually callability here. Here I have an example of an abstract callable. This is just some object I've created that has a call method, and you can interact with it by putting two parentheses after it with some input into that, and it gives you some output. Very simple and very straightforward. And I can play around with what that means, and I can look and see that it turns out there are a lot of things, a lot of objects in the Python language that respond to this protocol. There are C functions. There are custom functions that you've written. There are objects with call methods. Types themselves respond to it. That is, when you take the name of a type and you put parentheses after it, you get an instance of that type. It turns out that there are a lot of very fundamental things. This is one of the most fundamental ways for you to interact with an object in Python. The other very fundamental way to interact with an object in Python is through iterability. Now, in the same sense, I can create a custom object, and this is a custom iterable, and there's a couple of interesting notes here. The first note is that you'll see terms bandied around, iterator and iterable. And sometimes these terms can be somewhat confusing. An iterator is anything that you can iterate over. You have some object and you can get elements out of it in some order. And that order may not be fixed, but you can just get elements out of it. That's an iterable, rather. An iterator is merely something that can be iterated over that knows where it is in the iteration. So you have a list, and a list is an iterable. You can get every element out of the list. And when you type iter parentheses with the list inside, you'll get a list iter, and that's the iterator. That's the list itself and some idea of where you stopped in the computation. So here's an example of an iterable. And in the protocol, in order to encode this protocol, I encode iter and next, and you can see there's a note for Python 3, next has become underscore next, because it's now, in Python 3, a very fundamental part of the language. And here I just have some custom object that you can say, where are you in the iteration, give me the next element. Now, as a note, you can see that Python 3 is taking the idea of iterability to the next level. So one of the very superficial things they've done is what used to be izip and imap has now become zip and map. No longer are you restricting yourself to concrete iterables. You're now taking these more abstract versions of them and making them the standards. Additionally, if you look at some of the work that has been done on Tulip or Coroutines, they're very focused on iterators as a fundamental construct of the programs that you write. So, one step further, I know I'm rushing through this because I'm guessing you guys are all pretty solid Python programmers. But the next element over is we have generators. And sometime after the introduction of generators, there was a thought that these should be turned into coroutines. And if you go to Wikipedia and you look for coroutine, it'll give you a one sentence of what a coroutine is. And what it'll probably say is, a coroutine is a generalization of a subroutine. And this sounds really, really wild, but it actually kind of makes sense. In the first example, we saw a function, or a subroutine, and it had one entrance and one exit. You put some data into it, and it gives you some data, you're done. In the case of a coroutine, you have some structure where you put some data into it, and then you can pull results out of it as you iterate over it, as you desire them. And with a coroutine, you can actually put inputs right back in. So you now have some structure that can take inputs as you go and give you outputs corresponding to them. And we'll see later in this presentation ways that you can use this to model and structure some very nice, you can do some very nice modeling and structuring of problems. So part of this coroutine protocol, there are some methods on it. And I want to go very briefly and very quickly over the methods. The most basic is next. A coroutine is something that you can get elements out of. And there is an underscore next or a next method on all coroutines. And that just gives you the next element. Similarly, there is a dot throw. And this is something that very few people end up actually really using. You have to go pretty deep into some libraries to find people using dot throw. But essentially, you could think if you have a coroutine, if you have some piece of executable code that you can re-enter and reinsert input values into, you might want to insert an exception. You might need to have some mechanism for dealing with exceptions as well. And that's what dot throw is. Similarly, you might think that if we have some object that's sitting around that's representing a chunked or a delayed computation, you might want to tell it, stop, go away. And that's what that closes. But most interesting, and I'm leaving it for last, is dot send. And dot send is your way of reinserting inputs into this piece of executable code. So I'll show you this example here, and we'll dwell on this for just a second. This looks like a generator. You can see a yield statement that's allowing you to pull values out of it. And this yields very simple things. You start it with a value x, and then it yields x plus 1 and x plus 2. What it also can do is it can take inputs right back into it. And that's what's happening on the left-hand side of this y. This illustrates a couple of things. So we see how we actually call it. We take generator 10 that creates this instance of this computation with some starting value 10. And then we get g.next, which gives us 10 plus 1, 11, and also the value y, which should be none. But then, in the next step, we can send a value right back into this piece of code. So here, we're sending ABC back in. Well, send is actually a combination of pulling out the next value and putting in the next input. So what this does is it will put in ABC as y, and then we'll resume here. We'll get 12, and we'll get ABC as the next value. Now, there is one really nasty part of the syntax for generators. Here is a very simple coroutine. And you can see I'm not doing anything with the value that I could send back in. That's fine. And I'm trying to instantiate it and then send a 10 in. Where does that 10 go? When I instantiate it, I put this value here. And the next time I pull a value out, I'll get this x plus 1. But how do I put a value back in before I run the code here? Well, it turns out you can't. And it gives you this really nasty, really awful error. At PyTexas, when I gave this presentation, one of the core developers, Nick Coughlin, was in the audience. And when he looked at that, he said, you know, we really need to change this to an error message that people can actually understand. But you'll get this error message that says, can't send non-none value to a just start generator. The implication of this is whenever you see a library that uses generators heavily, you will almost certainly see something in there that's called prime or pump or something like that. And that's one way that we get around this nasty little piece, this nasty little syntactical restriction. I want to go on a slight divagation to talk about my 14th favorite library in the Python. Actually, this is my third, maybe my second out of 14 favorite libraries in the Python programming language, itertools. And it is a beautiful module that contains a lot of pieces that are very useful for dealing with abstract iterables, and namely generators. It is not itself a collection of generators. Itertools in CPython is written in C. And they're written in C as just normal CPython objects. Generator, in the context of Python, usually refers to a specific set of syntax. And itertools doesn't really fall under this category. But there are tools that are extremely useful for dealing with generators. Itertools is a combination of generalizations, algorithms, and helpers. When I say generalizations, we know that we can take Python lists like this, and we can slice them. We can get element 1 to element 4, or up to but not including element 5, and we can slice them. But you could think that we could take any sort of sequence, maybe a stream coming off of some data source, or a list, or something like that, and we might also want to get some slice of the elements. But we can't use this syntax on that. Itertools provides us with islice, and islice allows us to very nicely slice into any abstract iterable. So here I have a generator that yields numbers in the Fibonacci sequence. If you go to Reddit, if you go to R programming on Reddit, you'll see this in the sidebar. It's a very simple generator object. And you can see that I can actually slice into this using islice. So itertools contains generalizations. And you can see it contains things like imap, izip, imap, ifilter, and Python 2, which are generalizations on top of your simple map, zip, and filter. It also contains helpers. So we know we can concatenate two lists. And almost certainly, if we've ever written any Python code, we've tried to concatenate a list to some input data we've been given. And it turns out that somebody thought, oh, I can give a tuple just as easy as a list. And it barfs at you and says, you can't add a tuple to a list. And you can think, well, do I really want to force the person who's using this function to necessarily only send a list so I can concatenate these? No. In itertools, you have chain. And chain allows you to take anything that you can iterate over and just chain them together. It is extremely useful. And so you can see here, I can chain a 0 to the front of this. This is an infinite sequence, and I can chain a 0 to the front of it. Additionally, itertools contains things like t, repeat, cycle. At the giveaway, at the end of the day, I'll be live coding something where I'll use probably half of itertools to code a really neat little example. Additionally, itertools contains algorithms, like take while and drop while. So it's an algorithm in the sense that these are tools that can allow you to express views or computations on top of a sequence. So take while allows you to take a certain number of elements from an iterable until a predicate returns false. Drop while is the opposite. There's also product combinations. You have some combinatorial helpers in there as well. Now, the question is, why are we excited about generators outside of just being able to play with some syntax? And I think part of the answer is efficiency. And here is so I've structured this presentation to give you the worst answer first and the best answer second. So the worst answer is efficiency, sort of. Memory efficiency out of this bad answer is the better of the two. Namely, we're going to look at an example of something that you might want to build. And I call it pairwise. And this shows up all the time in the code that I write. It shows up constantly. Now, it may be my fault for trying to wedge every problem that I run into something that can use pairwise. I don't know. But all pairwise does is it takes some sequence that you give it, and it gives you pairs of it. So if you give it the numbers from 0 to 9, it'll give you 0, 1, 1, 2, 2, 3, 3, 4, and so on. And this is very useful if you want to calculate something like a moving average. You get a stream of data, and you take windows of 3, and you have the average over every 3 elements. And here it is encoded as a function. And you can see it works fine if I give it 10, but if I uncomment this line and I run this CPython notebook, I'm going to blow up. Because by virtue of being a function, it has to calculate everything eagerly. And I'm going to run out of memory way before I'm able to give you the pairwise of elements up to 1,000,000. However, you can think, for the example of a moving average, maybe I don't want the entire sequence at once. Maybe I only want every 3 elements, and I'll just spit them out to the display. So this is actually very wasteful. If I were to encode this as a generator, you can see that first, the code is much simpler, much shorter, much less convoluted. And now I can actually uncomment this and get each one of these elements. By virtue of being lazy, I can perform this computation without needing to allocate memory equal to the entire size of the computation that I need. In this case, I will only ever allocate 2 pieces of memory for 2 pairs, 1 for each of these. Because I'll generate this value, then wait for you to ask me for this value, then wait for you to ask me for this value, and I'll only ever need to hold one of those in memory at one time. Memory efficiency turns out to be one of the more compelling efficiency reasons to use generators. Now, as an example, and I'll show you this later, this is a way that you can write you can write nwise using helpers from itertools in a very compact and very efficient fashion. And it turns out to be somewhat intimidating to look at, but very easy to understand. Namely, what you do is you take some generator object and you t it, you make copies of it. And you take each of those copies and you stagger them. And then you zip them together. So you take 0 to 9, 0 to 9, 0 to 9. You stagger this so this is 1 to 9, and this is 2 to 9. And then you zip across 0, 1, 2, 2, 3, 4, and so on. So this is a very nice, very useful, and I end up having to type this from memory all the time in the code that I write. So let's take a look at efficiency from another perspective, time efficiency or processing efficiency. And I have an example for this that I don't really like, but I show anyway, because people like it. That's my claim. Namely, I have the same pairwise written in not very good C++. And I have it also written in reasonably okay Python. This is the same way that I wrote it before, but I could write this in a more expanded format as well. But this is my same naive combine pieces from itertools to write pairwise. And let's actually see what it does. So from 1 to 100, I'll do this from 1 to 10. The C++ version gives me 1, 2, 3, or rather it gives me 1, 2, 3, 2, 3, 4, and so forth and so on. And let's try this guy. They give me the same output. And now let's try timing them. And we'll bump this up to there. And we'll actually bump this up to, I think 1,000,000 is about where I want to be. And while that goes, I'll time it here. And it always gives me different results. But you can see the C++ version took 2.3 seconds. The Python version took 3 seconds. Is this a good example? It's a terrible example. Where is the actual processing time spent? Probably not in the parts that would actually make this useful. However, it is very rare that we can see naively written C++ code, or even decently written C++ code and naively written Python code that performs within the same order of magnitude. So there is something there, even if this isn't the most compelling example for that. However, so a friend of mine used to give a talk on number as a mechanism for optimization. And he would show different examples of how to code certain problems, like primality checking, using a simple approach in Python, my favorite generator to the max approach, and then approach using number. And so here you have a very simple trial division primality checker written in a combination of generator expressions and pieces like that. And here you have it written in kind of Python 101. And unfortunately, when we actually run this, you can see the timing of the fancy version is 2.2 microseconds, and the timing of the Python 101 version is 1.3 microseconds. So it turns out that in some cases, taking your code that looks like this, and you say, well, that's too elementary, let me spice it up a bit, and writing it like you'd be encouraged to write it given this presentation, may not actually yield any performance improvements. It turns out, however, that the reason that it doesn't yield performance improvements is that the cost of instantiating a generator instance overwhelms the cost of the total computation. So here I try to take the two pieces apart, and then I go down to 200 nanoseconds. It's not a very meaningful result, but it goes to show that in some cases writing dumb Python for efficiency can actually be faster than writing fancy generator-laden Python, because creating generator expressions tends to be actually a fairly time-consuming thing to do. However, I would say that the most compelling, from a perspective of efficiency, reason to use generators is how it improves the way that you model your code. Let's take the example of the 2x3s, the two ny's I wrote in C++ and in Python. When I write code in terms of generators, I tend to write them in very simple building blocks that have a very restricted API. As a consequence, it turns out to be extremely easy for me to take these building blocks and swap them out with something written in a more efficient way. And I'll show you an example. I have the same ny's, but it's now written as an extension object. And if you look at this code, it's about 111 lines of code. It is almost entirely boilerplate. It is maybe 10 lines of code you have to write yourself. And what you could think is, I might write this ny's in pure Python, and I say, well, this is actually where all the time of my program is going. This is a little bit slow. What I could do very easily, by virtue of having written my code in such a way that the interactions between the different pieces are so well defined, given that generators provide a very simplistic and stripped down API, I could just swap it out with the version written in C very easily without anybody noticing and get all the performance that would result thereof. I could write pieces of it in assembly, for example. And it turns out to be very, very easy to do. It is a very compelling approach for writing your code, structured in terms of generators, profile. If those generators are slow, rewrite them in C, and then you get a lot of performance back. However, what excites me the most about generators is not really the performance. If Dijkstra was still alive, he would frown at this obsession with performance. I think he would think it would be a little bit vulgar. He would worry about how you model your code and the correctness of your code. And I think that's where generators really shine. So the first part is very high level. Generators allow you to structure your code in terms of stream data processing. Namely, you have individual units that take input and then provide output, and you can chain them together. If any of you have ever been in a band, it's kind of like taking your guitar and plugging it into an amplifier and plugging it into something else and plugging it into something else. By virtue of each of these building blocks being lazy, you can then build a very nice whole computation where each piece just takes one piece of data, processes it, and sends it off down the chain. You could do nice things like sensor fusion, or you could simulate networks. You could do a lot of neat things, modeling things in terms of these little building blocks that are established in a pipeline. And the code will end up looking very similar to one programming approach that I think we all find to be very pleasurable to use, namely scripting at the command line, piping things from one input to another input to another input. That's how you can model your code with generators. And I think it's a very compelling way to write programs. However, I like to say that generators, as your key to nirvana, are your ability to free yourself from presumption. Many different presumptions. The first one is a presumption about return type. And this is the most simple one. Here I have my Fibonacci sequence. And this gives me Fibonacci numbers up to but not exceeding n. And I'm returning them as a list. But what if I wanted them as a set? Would I have to take this and put set there? What if I wanted them as a tuple? I have to take this and stick it into a tuple constructor. And I'd have to maintain memory for both of them. I'd have to maintain both of these structures in memory at the same time. So if this were very big and I were converting it to a tuple, I'd have to have them both in memory at the exact same time, because this couldn't be garbage collected until this tuple were constructed. So there's some memory pressure that I'm adding, and I'm also making some presumptions. And you can see I pay a penalty to convert it. Whereas, if I were to write this as a generator, I have now made no presumption about the return type that you want. I don't care if you want a list, a set, a tuple, who cares? And in this case, if you want a list, you say, I want a list, you take my results, you put them into a list. You want a set, you put them into a set. You want a tuple, you put them into a tuple. And in this case, you don't have to maintain any additional memory. You only maintain memory equal to one instance of each of these. And it turns out the timings are a little bit better. You gain a little bit of a time improvement from not having to do this duplicate construction of data structure. However, more interestingly, they free you from a presumption about return types. So here's something kind of tricky. When I write this Fibonacci, this little piece of code, I could return Fibonacci numbers up to but not exceeding the number n. So if you give me 20, I could return 3, 5, 8, 13, but the next one will be 21, so I'll stop at 13. Or I could return the first 20 values. So I'd keep going until I hit 20 values. And you could think, if I'm sitting here trying to write one of these functions, which one do I choose? Most likely, I'll choose both, and I'll end up with a really nasty signature that says up to but not including, and a bunch of flags here, and a bunch of nonsense that looks like that. I'll be encoding a lot of modalities into this code that may not be relevant to my programs. So you can see there are two different versions of the Fibonacci sequence. One that gives numbers, this is mislabeled, but this is numbers up to but not exceeding n, and this is the first n values. When I restructure this as a generator, I just return an infinite sequence, and I let the user decide which values he wants. So in this case, I'll use islice to get the first 20 values. And in this case, I'll use takewhile to get values not exceeding 20. I have now freed myself from a need to determine what values are produced and put that as a responsibility of the user of my function. And at the same time, dramatically simplified the code I have to write. Pretty good, huh? However, there's more. We can also free ourselves from the presumption of how the values are used. So I've taken the same Fibonacci sequence and I've added a sleep in there. And let's say I only want the first number. Or let's say that I ask for Fibonacci's up to 20, but I only want the first number that also happens to be a factor of something else. So I have to go through them. Well, here, I'm paying for the entire cost of all 20 sleeps, right? Because I need to get all of those values out eagerly. Whereas in the case of the generator, I only pay for the cost of the sleeps for the values that I actually need. So let's think about this in the construct of a large trading system. Say you have some complex object hierarchy representing the deals that you have in a trading book. And you have a trading book and you have a bunch of deals. And maybe you have a very high volume trading desk, so you have millions and millions of deals. What if somebody wants some subset of those deals and they want to look at them individually? Would you write that as a function that has to return a list of 1 million deals? Of course not, because you'd probably blow the amount of memory that they have available to them. If you wrote it as a generator, they could take as many of these objects, which may be loaded in the background lazily from some database or some object store. They could get every single one they want, and when they want to stop, they don't pay any of the computation that they don't need. generators allow you to not have to pay for computations that you don't need or you don't want or you won't use. And one example of this is business dates. Everybody writes business dates wrong for two reasons. One, there's always a while loop when calculating the next business day, which is wrong. There's a closed form solution for calculating business days, which I need to give a presentation on at some point. But also, usually, there's a holiday calendar sitting on some database somewhere. And the nth business day is written as a function. And you say, here's today, give me business day 2 in the future. And it goes off and it queries for the holiday calendar, comes back, and then does this little while loop. But you could think, what if I wanted the 2nd, the 5th, and the 7th business day from now? Do I call that function 3 times? I'm invoking three database calls. Whereas if I use my generator formulation, my generator can hold a handle to the open database. It can load all the data it needs. It can load the data lazily. And only as I ask for subsequent business days do I pay for the computation that's needed. So here's a more in-depth example of that. However, there's more. This is what really grinds my gears. Not this. Well, this does grind my gears. This is an example of what I said before, pumping and priming. This is a little messy thing that introduces the next segment, namely the knobs and the buttons and the modalities. All of us have written a piece of code, and we were very proud of what we wrote, and it was beautiful. And we sent it out to the world for other people to use. And somebody came back and said, well, could you add this to it? And you say, well, yeah, I'll just add another parameter. And somebody else asked for something, another parameter. And we end up with a function that has 20 different parameters, where subsets of those parameters don't really work with each other, and nobody really knows how to use it without just cutting and pasting how the other guy used it. You end up with this multiplication of these knobs, these modes, these parameters, these buttons. And I think this is one way that generators can free us. They can allow us to restructure our code in such a way that the modalities are encoded in the combinations and the compositions of the generator objects rather than in the functional units that we write ourselves. So I have this little pumped guy because it's necessary for the next piece. But here we have something very interesting. It's called predicate. And all it does is it takes some value and some end state. And what it does is it takes values until it hits that end state. So you tell it 30, and you give it some list of values, and it'll just take values from that until it hits 30. Very simple. Doesn't have any modality to it. And here I have something called greedy. Now what greedy does is it takes some set of values and it repeats them infinitely. And it takes values from this infinite sequence until a predicate says false. And then I just chain them together. Think about one of the simplest applications of a greedy algorithm. Counting change. How do you count change? Well, you imagine I have an infinite drawer of 25 cents, an infinite drawer of 10 cents, an infinite drawer of 5 cents, an infinite drawers of 1 cent. And I have a number in my mind for where I want to be, 32 cents. So I'll take 1 quarter. If I take the next quarter, nope. Then I'll take 1 dime, nope. I'll take 1 nickel, good. And I'll take 2 pennies, and I'm done. This is an encoding of this greedy algorithm for determining change. But it's encoded at such an abstract level that not only can I use it to solve change counting, where all I'm doing, the only real magic here, there's a lot of little pretty printing display stuff, but I've given it the denominations. I've told it run until it hits this amount, feed it into greedy with the coins reversed, and then it will calculate for me your change for this. Oops. Your change for this is this, and so forth and so on. I've put a little bit of effort into printing it nicely with little C's and whatnot. But very interestingly, this exact same problem is how you calculate Roman numerals to Western numerals, Arabic numerals, for determining dates, right? So I have the exact same code. Everything is the same here. And the predicate is, instead of being the amount of change you want, it's the year you want. And the inputs, instead of being the denominations you have, they're the Roman numerals you have. And with the exact same thing, I'm able to calculate a conversion between Gregorian dates to, or Gregorian years to Roman numeral years. So you can see that I've now fundamentally written code in a very different way. It's very abstract, and it really gets to the meat of what I want. I want some algorithm that just takes elements until it can no longer. That's literally what a greedy algorithm is. And I have some predicate that tells it when to stop. And I can apply it to a very wide range of different and very different looking problems, where the only difference between these two solutions are the inputs that I've given it. I've now liberated the programmer who's using my code to drive the solution he wants from his end. So, at the very end of today, I'm going to do something that I like to call the Showcase Showdown. And if any of you have ever been sick from school and turned on TV at 2 p.m., you would have seen The Price is Right, hosted back in my days by Bob Barker and now by Drew Carey, yeah. Very skinny Drew Carey, actually. It turns out that The Price is Right is a global phenomenon, which I didn't know. So it turns out that I speak Chinese, and The Price is Right also exists in China. This is the Chinese Bob Barker. And it's called 购物街, and the guy's name is Michael Bo, or something like that. So The Price is Right is actually a global phenomenon. So when I give this talk in different countries, I can actually often find their local version of The Price is Right to show them. But I thought the Chinese version would be the best, because it's wild stuff. I'll show you one more clip from that I got from YouTube. It's great. See, it's the exact same thing. And they have, they have 史料, they have Chinese numerals instead of Western numerals, all the same games. So what does this have to do with generators? Well, at the meetup group that I run, we get a lot of books from organizations like Pearson and O'Reilly, and we have to give them out. Right now, we give them out to people who give lightning talks, because we want to encourage people to come up on stage and give talks for the first time. Prior to that, what we do is we do a little bit of live coding to randomly select from the audience somebody who gets the prize. And we wanted to encode the little wheel from The Price is Right. And it started as something very simple that looked like this. And this is something that we'll see maybe later today. And in the next stage, I wrote a very simple Mersenne twister as a generator. You can see it's like 10 lines of code. It looks ugly because Mersenne twister is ugly. It has all of these bitwise anding, and that's just the way it looks. But I've written a Mersenne twister in 10 lines of code. That's the next step. And the next step was we wanted to simulate the wheel. The point was, when you see your name showing up on the screen, you want it to slow down, because that increases the tension and it gets people excited. You want to have to wait for that next name to come up, because it might be your name. And so the question was, could we do better? Because if you've ever seen the Showcase Showdown on The Price is Right, it's got a wheel with a flipper. And that flipper will sometimes cause the wheel to go backwards. And so what we wanted to do is we wanted to write a wheel that would spin your names, and then your name would come up, Kirat Singh, and you'd be like, oh my goodness, I got it. And then it would go backwards, and it would be the person right before you, Michael Naughton. So that I thought would be wild. And so how do we encode that, right? Well, the typical approach with object orientation is something like this. You have a wheel object, and it has a spin method. And it has all these different methods that try to approximate what a wheel looks like in reality. And I think that in literature, there is a term for something like this called the pathetic fallacy. It is the misattribution of human qualities to the inanimate. And I think that's one of the big problems with some of the approaches that we take to object orientation. We assume that we can model what reality looks like, and we get bogged down in all of the complexities of reality. So this solution turns out to be something that's fairly hard to test, that ends up being very complicated, and that ends up initially looking very similar to what the wheel would look like, but then drowns in the complexity as you want to add more features. So how do we do this better? Well, let's say that we implement this as 2 generators. The first generator is called wheel, and all it does is it takes some iterable, and it goes through the elements one by one. So if you give it 1, 2, 3, it'll do 1, 2, 3, 1, 2, 3, 1, 2, 3. It just imagines that the elements are on a little loop, and it'll just loop through them. And it has one more thing. It can go in either direction. So you can tell it to go backwards, and it'll go 3, 2, 1, 3, 2, 1, 3, 2, 1. And because it's a coroutine, midway through, you can tell it to change direction. So it goes 1, 2, 3, 1, 2, 3, and then you say send backwards, and it'll start going backwards. That's how you get the names to go backwards. And then you create a little guy here called spin. And all it does is take this little coroutine and just spins it, slowing it down based off of some transition function that gives you the velocity going down. But I thought there's still too many knobs here, because you can see a knob called velocity and stop and transition and all that nonsense. So how can we extract that one level more? One thing to say is, this thing is the wheel is such a simple little piece of code. All it does is it takes some input and goes through them in some order. So it's incredibly easy to write a test for it. The test for it is literally, you give it some input and you just check the next values. And you can check the direction is backwards. This guy actually takes a lambda as a direction, so you can check that it skips over elements. But look, this is the entirety of all the functionality that it exposes to you, which ends up to be very easy to exhaustively test. In the object-oriented solution, you'd have a lot of internal state that you couldn't track that might end up leaving you blind spots in what you're trying to test. The next thing that we could do is we might be able to modularize it more. We might be able to give it a velocity function. And all this function does is it takes some initial state and some end state and gives you values representing how the velocity changes over time, given some function that models friction. And this itself tends to be extremely easy to test as well, because all it is some function that starts with some value and needs to eventually get to 0 and transitions to it. So you can see here my test, I say, I can say, assert each element is it's monotonically non-decreasing, or sorry, monotonically non-increasing, decreasing. And you can see in this test, all I have to do is make sure it goes down to 0, and then it works, because it doesn't do much. And you can see in this case, it's actually going backwards, and then it goes down to 0 eventually, or close to 0. And if I put them all together, I end up with a guy that looks like this. So I have some spin function, some velocity function, and some wheel. All the wheel does is takes an iterable and goes through it in one direction or the other. It's a coroutine, so you can tell it to change directions mid-step. I have some guy called velocity that just gives you velocity values going down to 0, maybe in some nice curve, and you can model the curve. And think how easy it is to get this to fit very nicely to what you want it to look like, because it's just giving you the speeds, right? And by virtue of just giving you the speeds, you can very nicely see it and tweak it and have a very nice iterative design approach. And then I have some guy called spin that takes a wheel and a velocity, and it just goes through it and adds a little sleep command to sleep for amount of time to simulate that. And when I actually put it together, I get some players, some prizes, some winners. I get to shuffle them, and we end up kind of printing something like this. An IPython notebook, it doesn't work very well, but I end up printing it like that. And I end up with eventually somebody being the winner, or an error at the end. So this one had an error at the end. But I'll show you it in practice with a little bit of n curses magic. So this is what it looks like in practice. I don't know, sometimes it doesn't go backwards. We add a little bit of n curses to keep it all the screen at once. And you can see the numbers are just kind of circling around, and eventually it will slow down. We used to count people off, because at the meetup group we don't have a good RSVP list, so we just have to count people off and get their name, and it's slowing down. Oh my goodness, my heart's pumping. What's going to happen? Is it going to be me? And is it going to go backwards? I hope it does. It never goes backwards in the demos I give. Because it can't always go backwards, then you'd expect it. And then, oh, so excruciating, almost there. Oh, and the winner. So you can see that's a very interesting and very simple use of generators. So that is the end of my talk. I'm James Powell. I'd like to remind you to help control the pet population. Please remember to spay and neuter your pets. Thank you. So I think we have 5 minutes for questions. Anybody have any questions? Anne? So the question is principles on when not to use a generator. And I think that if your approach is, oh, I'm going to take some code that's slow and make it faster, generators may not always give you what you want. If your principle is, I want to take some code and think about the way I want to write it in a fundamentally different way. Instead of thinking in terms of these real-world objects, I want to think in terms of mathematical entities or entities that are very constrained, then I think that generators are a fairly good approach. Now you can see there's some operational complexity to using them. Pumping and priming is the most obvious one. The code itself takes a little bit of time to be able to read through effortlessly. It's something of a more novel approach to writing code. Not a lot of Python code gets written in this fashion. But outside of that, I don't think that there's any reason to explicitly not use a generator for any of the other reasons that I've given. Any other questions? In the back. Mark Higgins.
The syntax of the generator is a little bit more confusing than the sort of regular Python.
Yes, slightly. I would say in practice, I find that once you write generators for a couple weeks or some period of time, it just kind of, when I was first learning programming, the syntax for functions was beyond me. When I started using generators, the syntax for generators was beyond me. At some point, it's not rocket surgery, so it ends up being pretty straightforward. It's not brain science or rocket surgery. It ends up being a very useful and very immediately practical tool. Now I'll say that it's immediately practical for really fundamentally changing the way that you write your code. For writing your code in terms of very simple APIs. Like you can look, a generator can only do 2 things. You can call it to create an instance, and you can iterate over it. So you can think in the example of the wheel, right? The API that I provide for the wheel is going to have all these methods. And somebody's going to need a start the wheel and make spin backwards function and all these. And I feel that that's actually a lot more confusing because you end up with this long list of methods that needs to be documented. And people have to read the documentation to know how to use it. And nobody ever reads documentation anywhere. And so it ends up being very difficult for the user to end up using it. With a generator, you can't really abuse it because I'm giving you something, and all you can do is call it and find the next value, and that's it. So by virtue of having such a restricted API there, there's a limit in what you can do. And I'll give you a specific example of that. I once had an example where we had some code that needed to be interlaid with some other processing. And the way that we wanted to write is we want to write 3 functions. One that gets called at the beginning, one that gets called at every loading of some data in the background, and one that gets called at the end. And we thought, well, if I write 3 functions, what I'm telling a user who sees these 3 functions in the library is that there are just 3 functions here. And you have to read the documentation to know, don't call number 3 unless you've called number 1, and call number 2 in the middle. But a generator, very naturally, via syntax, allows you to give that restriction to the user. Namely, you put the code that you want at the top, then you put a yield, then you put the next piece of code with a yield in a for loop or a while loop, and then you put the last piece of code there. And now I'll give you a piece of code. I'll give you a little object. And that object, you can only ever call these computations in the order that's specified, because all you can do with it is instantiate it, go through the next values. So in some way, generators can actually substantially simplify the API that you present to your users. Any other questions? Otherwise, we should. I have to make sure that I'm on time, because that would be so hypocritical if I've sped up the last speakers.
Don't you think this would be a bit more opaque? Because I mean, Python,
My talk could be more opaque, or because I think I did a pretty good job here of making it.
But you are struggling. I mean, it's hard to make this very transparent. I mean, coming from Java, where everything is really set out, to Python, where everything's kind of here. I got generators, and it just feels like another level of abstraction. Do you feel though sometimes that it actually makes it a little more difficult to kind of figure out? I don't know what you're returning with all these generators, and the kind of, I mean.
So I can tell you, when you look into depth of what a generator is, or if you look into the depths of CPython, you'll find that it ends up being a fairly simple set of manipulations on structures in C. So a generator behind the scenes is really just some object that maintains some internal state that has some way to start the iteration, to instantiate it, and some method to get the next value. And the very first example I showed you on it had an iter method and a next method. The iter method starts the iteration, gets everything signed up, and then the next method gives you the next value. And all a generator really is some object that has those 2 methods. It's a protocol, right? The advantage of generators is not really that you have this protocol, because you could write custom objects, and instead of calling it iter and next, you could call it whatever you wanted. And you could interact with them in your program in that fashion. And in a Java program, you'd end up creating these ad hoc protocols yourself. What Python gives you is a set of very standardized, somewhat ad hoc protocols that you don't have to invent yourself, that you can make use of, that if you make use of, constrain your options to something that's simple enough for people to use. And I'll give you an example of that. In Python, there's this object model function called call, right? And that lets you give an object, take an instance of an object and put parentheses after it and call it like it's a function. This exists in Java. But in Java, you'll call it run, or you'll call it execute, or you'll call it some name, right? And you'll have a visitor or observable pattern or something like that. And you'll tell people, well, I have all these methods need to inherit from this, and it has this method, and you have to call this method, right? So you have to read documentation to know what this run, or what this visit, or what this execute method is called. In Python, you implement underscore call underscore, and then everybody knows how to actually invoke it, because the syntax is always the same. You don't have to add your own protocol with its own documentation and its own qualifications. Generator is an example of this. They are a common structure that you see throughout your code that are simplified to a protocol that you can make use of, that when people are given a generator, they can only do 2 things with it, right? So in some sense, it tends to be a simplification on even what Java gives you. Now, the internal workings of them may seem complex. I think if you dive in and look at how generators work internally in CPython, it ends up being very, very simple. And that's another talk that I give, and I was actually going to give it at this conference, but we found much better speakers to fill in for me. But maybe if we hadn't found such wonderful speakers as we had for this conference, you may have seen some internal details of how generators work, and you can see how incredibly simple they are, even internally.
You find people who are very familiar with them, if you look at their code, they try to refactor most of it to generate, but the concepts and the principles are always there usually?
Yes, I think that what you're seeing is you can write some code in some number of lines of Java, and I can write code that accomplishes the same problem. So what we can think here is that we have 2 encodings of the same model solving the same problem. And I think that in Python using generators, you get some human advantages of maybe shorter code or code that's a little bit easier to release for other people to use because the APIs are simpler. But it's not that I'm doing anything that you couldn't do. I'm just being given structures to build upon that make things simpler in the end. So I think we're out of time. We have the next speaker. Maybe one more question, I don't know. It's up to you. I'm in the back. So that's exactly what a generator really is. So if you look internally, a generator is just a function that keeps two things. It has a code object and a frame object. And the frame object is the state. What a generator is some object that has a very restricted protocol where the state is the actual frame of the running code. So all the state is actually encoded, not in self.x or self.y, but in local variables in the frame, in the stack frame, but it's not on a stack, but in the frame, right? So that's what a generator is. It's a way for you to have a function that maintains state over multiple invocations. I think that's all for questions. I hope you enjoyed this talk. I will be doing a little bit of live coding at the end where we're going to be giving away, I think we have 50 books to give away. So definitely stay to the end. Also, there's an open bar event down the street. So stay for the end for some books and for some liquor. And eat more pies. They are delicious. Thank you so much.